Now we go just one step beyond circular motion and talk about a solid object rotating. So just to keep things simple, let's say we have a disk and it's rotating and the axis of rotation is perpendicular to the blackboard here. First, how do we talk about rotations? How do we describe rotations? It's very similar to the way we describe linear meters per second kind of motion. We define a positive direction and a negative direction, and positive angles are always counterclockwise away from some reference direction, and usually horizontal straight to the right we call the reference direction, and then any angle counterclockwise from that is a positive angle. And important, whenever we're working with numbers, we always name these angles in radians, not degrees. So imagine, so now instead of a position that we identify along a straight line, a position that we identify with a certain number of meters away from the origin of the coordinate system, now we have an angular location a certain number of radians away from the origin of the coordinate system. Right? All points on this radius of the disk are theta 1 radians away from 0, and all points on this radius are theta final radians away from the 0. So let's say there's a rotation counterclockwise starting such that all these points along this radius rotate that much. So then the change in the angular location is just like changing anything else, final angle minus initial value. And then we define the rate of change in angular location. And just as the rate of change in plain old meters type location is velocity, the rate of change in angular location is angular velocity. This, don't call this a W, this is lowercase Greek letter omega. And like regular meters per second velocity, it's a vector, so it has a direction. But the way we define it looks very, very much like the way we defined a linear meters per second velocity. Right? Change in location divided by the length of time it took to make that change in location. And now think just a little bit about direction of angular velocity. We'll consider only simple cases where the rotating object always rotates around the same axis of rotation, right? The rotation axis doesn't twist around. The rotation axis here is always going to be perpendicular to the blackboard. We always say that an angular velocity points along the axis of rotation. So it would be just two possibilities, this way or this way. And we'll refer to this way out of the blackboard or out of the paper pointing towards you, that's the positive direction, and into the blackboard away from you, the negative direction. And what we see then is if we have a counterclockwise rotation, then because we defined increasing angular location going this way, and so decreasing angular location would be going this way. Any counterclockwise rotation would be moving from a smaller angular location to a bigger angular location. So the change in angular location, we could call it angular displacement, the change in angular location is positive. So if that's positive, angular velocity is positive. Angular velocity points in the positive direction, which we're always going to define as this way. And then, other way around, if you have a clockwise rotation, that means you're starting at one angular location and moving towards a smaller or more negative angular location. So the change in angular location is negative. And so if that's negative, then angular velocity is negative, which will point that way along the axis of rotation. So just to say it more concisely, a clockwise rotation corresponds to negative angular velocity, and then a counterclockwise rotation corresponds to a positive angular velocity. And then, of course, just like we had in the linear case, we want to talk about the rate of change of angular velocity. The rate of change of old-fashioned linear meters per second velocity was acceleration in meters per second. Similarly, we can talk about change in angular velocity and the rate of change in angular velocity. And the rate of change in angular velocity is what we'll call angular acceleration. And the definition for angular acceleration looks very much like the definition for meters per second acceleration. It's change in velocity, this time angular velocity, divided by the length of time it took to make that change. And this is lowercase alpha, Greek letter alpha. That'll be our symbol for angular acceleration. Now, go back and remember something else from our talk about velocity and acceleration. Think about change in the velocity. It's always final minus initial velocity. And I can rewrite that as initial angular velocity plus change in angular velocity equals final angular velocity. In just the same way that we said an ordinary meters per second velocity plus a change in velocity equals a final meters per second velocity. So in other words, just as this delta V represented some extra velocity that you added on to an initial velocity in order to get a different velocity, delta omega represents the change in angular velocity that you, some extra angular velocity that you add on to the initial angular velocity in order to get a different angular velocity at some later time. And just like in the case of regular acceleration, where this equation, the definition of regular acceleration tells us that the direction of this vector has to be the same as the direction of this vector. That is, the direction of the meters per second acceleration is the direction of delta V. In other words, direction of acceleration is the direction of the extra velocity that's added on. Exactly the same thing happens here when we're talking about angular velocity and angular acceleration. Our definition of angular acceleration tells us that this vector has to have the same direction as this vector in order for those two vectors to be equal. So the direction of angular acceleration is the same as the direction of the extra angular velocity added on in order to make velocity change. Well, velocities point only one way or the other along the axis of rotation, so then any extra velocity added on must point only one way or the other along the axis of rotation. And if angular acceleration is the same direction as this, then angular acceleration must point only one way or the other along the axis of rotation. Just look at a couple examples of this. Let's say you've got something rotating counterclockwise and speeding up. Well, counterclockwise rotation, we've already established that that corresponds to a positive angular velocity. And speeding up means that positive angular velocity is getting stronger and stronger as time goes by. You've got a bigger positive angular velocity as time goes by, which means you had to add more positive velocity. The velocity added on is positive velocity. You're adding positive velocity onto velocity that's positive, so you get bigger, stronger, faster velocity. Since the direction of acceleration tells you the direction of the velocity added on, acceleration is positive, and that's the same kind of thing we've seen before. Whenever you speed up, velocity and acceleration point the same way. Now, just let's imagine now clockwise rotation and speeding up. Clockwise rotation, the opposite kind of rotation from this, would mean the angular velocity is in the opposite direction. We've already established that clockwise rotations correspond to negative angular velocity. And that is an angular velocity that points this way, away from us, along the axis of rotation. And you've got negative velocity and you're speeding up. In other words, you're going to move faster and faster and faster in the negative direction. You've got stronger and stronger motion in the negative direction. More and more motion in the negative direction, which means you're adding more negative velocity on top of the velocity that was already negative. The velocity added on is negative, and acceleration points the same way as the velocity added on. And again, we see another example of what we've already seen ever since August. When you're speeding up, velocity and acceleration point in the same direction. And if you work through the other examples, like say clockwise rotation and slowing down, or counterclockwise rotation and slowing down, you'll see again that slowing down always corresponds to velocity and acceleration pointing in opposite directions. All right, and again, just like what we've already seen before, when there's an acceleration, there's something that's causing that acceleration. When we have a meters per second acceleration, we say net force causes that acceleration. And similarly, when we have an angular acceleration, there will be a net something else that causes that angular acceleration. So, net force will always cause, if there is a net force, that always implies there is a meters per second acceleration. And similarly, there's this thing that we call torque. And the net torque, whatever that is, we'll get to that in a minute, but whatever that is, if there is a net torque, that causes angular acceleration. So torque, whatever that is the rotational version of force. It's the thing that causes acceleration. Now, what is torque? Well, just like force, it's going to be a vector. And let's think of that in two pieces here: magnitude of the vector and direction of the torque vector. First, magnitude. Here's our rule for calculating the magnitude or the strength of a torque. Magnitude, size, strength, absolute value of a torque, has several factors. First, in order to have a torque, you have to have a force. And one factor will be the magnitude of that force. And then the next factor will be something that you could call a displacement or a distance vector, or something like that. The book uses the symbol R for this distance because it's usually, you can usually think of it as the radius of a circle, but I'm going to call it D because what it really is a displacement, and I think it's more helpful to think of it as a displacement from one point to another point. What those points are, we'll get to that in just a second. And then sine of an angle, and what that angle is, we'll get to that in just a second. So imagine a door, and the door is sitting still, but you're trying to open it. In other words, you want to change its rotational. You want to change its angular velocity. When the door is just sitting there, the angular velocity is 0. When you're pushing on it to open it, the angular velocity is not 0. So in other words, you want to change the angular velocity. In other words, you want to produce an angular acceleration. So in order to produce angular acceleration, there has to be a torque. Let's see how that works. Here's the hinge about which the door rotates. Here's the door. Here's the door knob. And let's say you push on the doorknob like you would normally, but instead of normally pushing perpendicular to the door, let's say you push at an angle. So here's the force with which you push. And there's the direction of the push, not perpendicular to the door. So that's force. This displacement D is always a displacement from some reference point to the point where the force is applied. So it's a displacement that's going to end up here and starts at some reference point that you choose. But usually the simplest place to choose that reference point is right at the axis of rotation. So there's the reference point at the axis of rotation. The door, when it moves, will rotate about this axis. And then this displacement vector, remember the book calls it R, is a displacement from the reference point to the point where the force is applied. So that's the displacement vector. And then the magnitude of that displacement vector is just the width of the door, which I'll call it just plain D. And then finally, angle. Angle, it's best if you remember a slogan when thinking about the angle. The angle is always the angle from the displacement direction. Here's the displacement direction in this case, to the force direction. there's the angle for this particular case. Now let's look at a whole bunch of different ways to open this door with different torques, just to see how this stuff works. Case A, simple case. We push right at the doorknob and we push in the normal way, perpendicular to the door. So there's the force. There's the point where we're applying the force. So the displacement vector is a displacement from the reference point to the point where the force is applied. And then the angle between the displacement direction and the force direction is just that angle. It's 90 degrees in this case. So in this case, the magnitude of the torque for situation A is just magnitude of the force, magnitude of D, times, that last term is sine of 90 degrees. Sine of 90 degrees turns out to be positive 1. So that's the torque in case A. Now, case B, let's imagine same door, and again we'll push on the doorknob, but this time, just like here, we'll push at an angle. So we'll push like that, at an angle like that. And let's say this angle, the angle between my push and the door, is 60 degrees. And then here's the displacement vector, taking you from the axis, from the reference point to the point where the force is applied. And then there's the direction of the displacement vector, and the angle from direction of displacement to direction of force is this angle here. And geometry tells us those two angles are equal, so this is 60 degrees also. So in this case, the magnitude of the torque is same force as before, same magnitude for the displacement vector as before. The one difference is now that the angle is 60 degrees instead of 90. So the last factor here is sine of 60 degrees. Your calculator will tell you that that is about 0.87. All right, now, another one. Let's say same door, case C, same door, and again, just like in case A, I'll push perpendicular to the door, but now I'll push in the middle of the door instead of out here at the end. So same force, but now the displacement vector is different. Here's the reference point, here's the point where the force is applied right in the middle of the door, so the displacement vector is that. It's only half as big as it was in the first two cases. So now, magnitude of the torque here in case C is same force, but the displacement vector is only half as big. It's only half the width of the door, so d over 2. And then sine of the angle between displacement direction and force direction. The angle between displacement direction and force direction is, just like in case 1, 90 degrees. And then the last factor, sine of that angle, sine of 90 degrees is, again, 1. So that's the torque in case C. Now, another one, case D, hinge, door, doorknob, and I'll push on the doorknob again. But just like in case B, I'll push at an angle. So here's the direction of the force this time. same magnitude for the force, but now in a different direction. And I'm pushing on the doorknob just as before, so the displacement takes me from my reference point to the doorknob, just like before. And then that means, in this case, the angle between the displacement direction and the force direction is that angle. And let's say that this angle here is 30 degrees. So this angle here is 30 degrees. And then this angle here, the angle between displacement and force, is 180 degrees minus 30, or 150 degrees. So torque, in that case, has a strength of same force, the magnitude of this displacement vector is back to plain old d, and now sine of the angle between displacement and force is sine of 150 degrees. And if you ask your calculator what that is, it'll tell you that sine of 150 degrees is 1/2. So there. Now let's just look at one last one. Case E. Now we'll move over here to some more different blackboard space. Same door, same force, pushing perpendicular, but now let's imagine a silly kind of situation that you would never do in real life, and this will explain why you would never do it. Push at the hinge. So in that case, the torque for case E is same force, but now think about the displacement vector. The displacement vector takes you from the reference point to the point where the force is applied. Those are the same point in this case, so that's no displacement at all. You don't move at all to get from the reference point to the point where the force is applied. A displacement of 0. Right. No torque in that case. In other words, no angular acceleration is produced. In other words, the door stays the same. It maintains the same angular velocity, namely 0. You can't open it. Well, let's look at, let's rank them all now. The biggest to the, or strongest to the weakest torque. Obviously, that's the weakest. Strongest was just case A. And then the second strongest was case B, 87% of case A. And then cases C and D are both half as strong as case A. They're both FD over 2. And then, of course, case E was the weakest torque, 0 torque. So you get the strongest torque, and since torque causes angular acceleration, you have the same sort of thing as you have with Newton's second law. Stronger net force gives you stronger acceleration, and in this case, stronger net torque gives you stronger, bigger angular acceleration. So this gives you the most angular acceleration. In other words, it's the easiest and quickest way to make the door start rotating and open the door. And this pushing on the doorknob, but not pushing not pushing perpendicular to the door, gives you a weaker torque, which means less angular acceleration. And what that means is that it's a little harder to open the door. And here, pushing either pushing on the doorknob at a funny angle or pushing in the middle of the door also gives you a weaker torque, smaller torque, which gives you smaller angular acceleration, which means the door opens more slowly unless you push harder. And of course here, it's a crazy place to push because it gives you no torque at all, which means there's no angular acceleration, which means the door maintains constantly the same angular velocity, which is 0 in this case. The door never opens. Okay, everything else we do with torque is just nothing but an elaboration of these ideas. For right now, all we're doing is just getting used to those ideas before we actually apply them in some different circumstances.